13 years later, in 1929, the American astrophysicist Edwin P. Hubble discovered that the universe is not static. He had found and assembled convincing evidence that the more distant a galaxy, the faster the galaxy recedes from the Milky Way. In other words, the universe is expanding. Now, embarrassed by the cosmological constant, which corresponded to no known force of nature, and by the lost opportunity to have predicted the expanding universe himself, Einstein discarded lambda entirely, calling it his life's greatest blunder. By yanking lambda from the equation, he presumed its value to be zero, such as in this example. Assume A equals B plus C. If you learn later that A equals 10 and B equals 10, then A still equals B plus C, except in that case C equals 0, and it's rendered unnecessary in the equation. But that wasn't the end of the story. Off and on over the decades, theorists would extract lambda from the crypt, imagining what their ideas would look like in a universe that had a cosmological constant. 69 years later, in 1998, science exhumed lambda one last time. Early that year, remarkable announcements were made by two competing teams of astrophysicists, one led by Saul Perlmutter of Lawrence Berkeley National Laboratory in Berkeley, California, and the other co-led by Brian Schmidt of Mount Stromlo and Siding Spring Observatories in Canberra, Australia, and Adam Rees of the Johns Hopkins University in Baltimore, Maryland. Dozens of the most distant supernovas ever observed appeared noticeably dimmer than expected, given the well-documented behavior of this species of exploding star. Reconciliation required that either those distant supernovas behaved unlike their nearer brethren, or they were as much as 15% farther away than where the prevailing cosmological models had placed them. The only known thing that naturally accounts for this acceleration is Einstein's lambda, the cosmological constant. When astrophysicists dusted it off and put it back into Einstein's original equations for general relativity, the known state of the universe matched the state of Einstein's equations. The supernovas used in Perlmutter's and Schmidt's studies are worth their weight in fusionable nuclei. Within certain limits, each of those stars explodes the same way, igniting the same amount of fuel, releasing the same titanic amount of energy in the same amount of time, thereby reaching the same peak luminosity. Thus, they serve as a kind of yardstick or standard candle for calculating cosmic distances to the galaxies in which they explode, out to the farthest reaches of the universe. Standard candles simplify calculations immensely. Since the supernovas all have the same wattage, the dim ones are far away and the bright ones are close by. After measuring their brightness, a simple task, you can tell exactly how far they are from you and from one another. If the luminosities of the supernovas were all different, you could not use brightness alone to tell how far away one was in comparison with another. A dim one could be either a high wattage bulb far away or a low wattage bulb close up. All fine, but there's a second way to measure the distance to the galaxies: their speed of recession from the Milky Way. Recession that's part and parcel of the overall cosmic expansion. As Hubble was the first to show, the expanding universe makes distant objects race away from us faster than nearby ones. So, by measuring a galaxy's speed of recession, another simple task, one can deduce a galaxy's distance. If those two well-tested methods give different distances for the same object, something must be wrong. Either the supernovas are bad standard candles, or a model for the rate of cosmic expansion as measured by galaxy speeds is wrong. Well, something was wrong. It turned out that the supernovas were splendid standard candles, surviving the careful scrutiny of many skeptical investigators. And so astrophysicists were left with a universe that had expanded faster than we thought, placing galaxies farther away than their recession speed would have otherwise indicated. And there was no easy way to explain the extra expansion without invoking lambda, Einstein's cosmological constant. Here was the first direct evidence that a repulsive force permeated the universe, opposing gravity, which is how and why the cosmological constant rose from the dead. Lambda suddenly acquired a physical reality that needed a name, and so dark energy took center stage in the cosmic drama, suitably capturing both the mystery and our associated ignorance of its cause. Perlmutter, Schmidt, and Rees justifiably shared the 2011 Nobel Prize in Physics for this discovery. The most accurate measurements to date revealed dark energy as the most prominent thing in town, currently responsible for 68% of all the mass energy in the universe. Dark matter comprises 27%, with regular matter comprising a mere 5%. The shape of our four-dimensional universe comes from the relationship between the amount of matter and energy that lives in the cosmos and the rate at which the cosmos is expanding. A convenient mathematical measure of this is omega, yet another capital Greek letter with a firm grip on the cosmos. If you take the matter-energy density of the universe and divide it by the matter-energy density required to just barely halt the expansion, known as the critical density, you get omega. Since both mass and energy cause space-time to warp or curve, omega tells us the shape of the cosmos. If omega is less than 1, the actual mass energy falls below the critical value, and the universe expands forever in every direction for all of time, taking on the shape of a saddle in which initially parallel lines diverge. If omega equals 1, the universe expands forever, but only barely so. In that case, the shape is flat, preserving all the geometric rules we learned in high school about parallel lines. If omega exceeds 1, parallel lines converge and the universe curves back on itself, ultimately recollapsing into the fireball whence it came. At no time since Hubble discovered the expanding universe has any team of observers ever reliably measured omega to be anywhere close to 1. Adding up all the mass and energy their telescopes could see, and even extrapolating beyond these limits, dark matter included, the biggest values from the best observations topped out at about omega equals 0.3. As far as observers were concerned, the universe was open for business, riding a one-way saddle into the future. Meanwhile, beginning in 1979, the American physicist Alan H. Guth of the Massachusetts Institute of Technology and others advanced an adjustment to the Big Bang theory that cleared up some nagging problems with getting a universe to be as smoothly filled with matter and energy as ours is known to be. A fundamental byproduct of this update to the Big Bang was that it drives omega toward 1, not toward a half, not toward 2, not toward a million, toward 1. Hardly a theorist in the world had a problem with that requirement, because it helped get the Big Bang to account for the global properties of the known universe. There was, however, another little problem. The update predicted 3 times as much mass energy as observers could find. Undeterred, the theorists said the observers just weren't looking hard enough. At the end of the tallies, visible matter alone could account for no more than 5% of the critical density. How about the mysterious dark matter? They added that too. Nobody knew what it was, and we still don't know what it is, but surely it contributed to the totals. From there, we get 5 or 6 times as much dark matter as visible matter. But that's still way too little. Observers were at a loss, and the theorists answered, keep looking. Both camps were sure the other was wrong, until the discovery of dark energy. That single component, when added to the ordinary matter and the ordinary energy and dark matter, raised the mass energy density of the universe to the critical level, simultaneously satisfying both the observers and the theorists. For the first time, the theorists and observers kissed and made up. Both, in their own way, were correct. Omega does equal 1. Just as the theorists demanded of the universe, even though you can't get there by adding up all the matter, dark or otherwise, as they had naively presumed. There's no more matter running around the cosmos today than had ever been estimated by the observers. Nobody had foreseen the dominating presence of cosmic dark energy, nor had anybody imagined it as the great reconciler of differences. So what is this stuff? Nobody knows. The closest anybody has come is to presume dark energy is a quantum effect, where the vacuum of space, instead of being empty, actually seethes with particles and their antimatter counterparts, They pop in and out of existence in pairs and don't last long enough to be measured. Their transient existence is captured in their moniker, virtual particles. The remarkable legacy of quantum physics, the science of the small, demands that we give this idea serious attention. Each pair of virtual particles exerts a little bit of outward pressure as it ever so briefly elbows its way into space. Unfortunately, when you estimate the amount of repulsive vacuum pressure that arises from the abbreviated lives of virtual particles, the result is more than 10 to the power 120 times larger than the experimentally determined value of the cosmological constant. This is a stupidly large factor, leading to the biggest mismatch between theory and observation in the history of science. Yes, we're clueless, but it's not abject cluelessness. Dark energy is not adrift with nary a theory to anchor it. Dark energy inhabits one of the safest harbors we can imagine, Einstein's equations of general relativity. It's the cosmological constant. It's lambda. Whatever dark energy turns out to be, we already know how to measure it and how to calculate its effects on the past, present, and future of the cosmos. Without a doubt, Einstein's greatest blunder was having declared that lambda was his greatest blunder. And the hunt is on. Now that we know dark energy is real, teams of astrophysicists have begun ambitious programs to measure distances and the growth of structure in the universe using ground-based and spaceborne telescopes. These observations will test the detailed influence of dark energy on the expansion history of the universe, and will surely keep theorists busy. They desperately need to atone for how embarrassing their calculation of dark energy turned out to be. Do we need an alternative to GR? Does the marriage of GR and quantum mechanics require an overhaul? Or is there some theory of dark energy that awaits discovery by a clever person yet to be born? A remarkable feature of lambda and the accelerating universe is that the repulsive force arises from within the vacuum, not from anything material. As the vacuum grows, the density of matter and familiar energy within the universe diminishes, and the greater becomes lambda's relative influence on the cosmic state of affairs. With greater repulsive pressure comes more vacuum, and with more vacuum comes greater repulsive pressure, forcing an endless and exponential acceleration of the cosmic expansion. As a consequence, anything not gravitationally bound to the neighborhood of the Milky Way galaxy will recede at ever-increasing speed as part of the accelerating expansion of the fabric of spacetime. Distant galaxies, now visible in the night sky, will ultimately disappear beyond an unreachable horizon, receding from us faster than the speed of light. A feat allowed not because they're moving through space at such speeds, but because the fabric of the universe itself carries them at such speeds. No law of physics prevents this. In 1 trillion or so years, anyone alive in our own galaxy may know nothing of other galaxies. Our observable universe will merely comprise a system of nearby long-lived stars within the Milky Way, and beyond this starry night will lie an endless void. Darkness in the face of the deep. Dark energy, a fundamental property of the cosmos, will, in the end, undermine the ability of future generations to comprehend the universe they've been dealt. Unless contemporary astrophysicists across the galaxy keep remarkable records and bury an awesome trillion-year time capsule, post-apocalyptic scientists will know nothing of galaxies, the principal form of organization for matter in our cosmos, and will thus be denied access to key pages from the cosmic drama that is our universe. Behold my recurring nightmare. Are we, too, missing some basic pieces of the universe that once were? What part of the cosmic history book has been marked access denied? What remains absent from our theories and equations that ought to be there, leaving us groping for answers we may never find? Chapter 7. The Cosmos on the Table. Trivial questions sometimes require deep and expansive knowledge of the cosmos just to answer them. In middle school chemistry class, I asked my teacher where the elements on the periodic table came from. He replied, Earth's crust. I'll grant him that. It's surely where the supply lab gets them, but how did Earth's crust acquire them? The answer must be astronomical. But in this case, do you actually need to know the origin and evolution of the universe to answer the question? Yes, you do. Only 3 of the naturally occurring elements were manufactured in the Big Bang. The rest were forged in the high-temperature hearts and explosive remains of dying stars, enabling subsequent generations of star systems to incorporate this enrichment, forming planets, and in our case, people. For many, the periodic table of chemical elements is a forgotten oddity, a chart of boxes filled with mysterious cryptic letters last encountered on the wall of high school chemistry class. As the organizing principle for the chemical behavior of all known and yet to be discovered elements in the universe, the table instead ought to be a cultural icon, a testimony to the enterprise of science as an international human adventure conducted in laboratories, particle accelerators, and on the frontier of the cosmos itself. Yet, every now and then, even a scientist can't help thinking of the periodic table as a zoo of one-of-a-kind animals conceived by Dr. Seuss. How else could we believe that sodium is a poisonous reactive metal that you can cut with a butter knife, while pure chlorine is a smelly, deadly gas, yet when added together, they make sodium chloride, a harmless, biologically essential compound better known as table salt? Or how about hydrogen and oxygen? One is an explosive gas and the other promotes violent combustion, yet the two combined make liquid water, which puts out fires. Amid these chemical confabulations, we find elements significant to the cosmos, allowing me to offer the periodic table as viewed through the lens of an astrophysicist. With only one proton in its nucleus, hydrogen is the lightest and simplest element, made entirely during the Big Bang. Out of the 94 naturally occurring elements, hydrogen lays claim to more than 2/3 of all the atoms in the human body, and more than 90% of all atoms in the cosmos, on all scales, right on down to the solar system. Hydrogen in the core of the massive planet Jupiter is under so much pressure that it behaves more like a conductive metal than a gas, creating the strongest magnetic field among the planets. The English chemist Henry Cavendish discovered hydrogen in 1766 during his experiments with H2O. Hydrogenous is Greek for water forming, but he's best known among astrophysicists as the first to calculate Earth's mass after having measured an accurate value for big G, the gravitational constant in Newton's famous equation. Every second of every day, 4.5 billion tons of fast-moving hydrogen nuclei are turned into energy as they slam together to make helium within the 15 million degree core of the Sun. Helium is widely recognized as an over-the-counter low-density gas that, when inhaled, temporarily increases the vibrational frequency of your windpipe and larynx, making you sound like Mickey Mouse. Helium is the second simplest and second most abundant element in the universe. Although a distant second to hydrogen in abundance, there's 4 times more of it than all other elements in the universe combined. One of the pillars of Big Bang cosmology is the prediction that in every region of the cosmos, no less than about 10% of all atoms are helium, manufactured in that percentage across the well-mixed primeval fireball that was the birth of our universe. Since the thermonuclear fusion of hydrogen within stars gives you helium, some regions of the cosmos could easily accumulate more than their 10% share of the stuff. But as predicted, no one has ever found a region of the galaxy with less. Some 30 years before it was discovered and isolated on Earth, astronomers detected helium in the spectrum of the Sun's corona during the total eclipse of 1868. As noted earlier, the name helium was duly derived from Helios, the Greek sun god, and with 92% of hydrogen's buoyancy in air, but without its explosive characteristics, helium is the gas of choice for the outsized balloon characters of the Macy's Thanksgiving Day Parade, making the department store second only to the U.S. military as the nation's top user of the element. Lithium is the third simplest element in the universe, with 3 protons in its nucleus. Like hydrogen and helium, lithium was made in the Big Bang. But unlike helium, which can be manufactured in stellar cores, lithium is destroyed by every known nuclear reaction. Another prediction of Big Bang cosmology is that we can expect no more than 1% of the atoms in any region of the universe to be lithium. No one has yet found a galaxy with more lithium than this upper limit supplied by the Big Bang. The combination of helium's upper limit and lithium's lower limit gives us a potent dual constraint on tests for Big Bang cosmology. The element carbon can be found in more kinds of molecules than the sum of all other kinds of molecules combined. Given the abundance of carbon in the cosmos, forged in the cores of stars, churned up to their surfaces, and released copiously into the galaxy, a better element does not exist on which to base the chemistry and diversity of life. Just edging out carbon in abundance rank, oxygen is common too, forged and released in the remains of exploded stars. Both oxygen and carbon are major ingredients of life as we know it. But what about life as we don't know it? How about life based on the element silicon? Silicon sits directly below carbon on the periodic table, which means, in principle, it can create the same portfolio of molecules that carbon does. In the end, we expect carbon to win because it's 10 times more abundant than silicon in the cosmos, but that doesn't stop science fiction writers who keep exobiologists on their toes, wondering what the first truly alien silicon-based life forms would be like. In addition to being an active ingredient in table salt, sodium is the most common glowing gas in municipal street lamps across the nation. They burn brighter and longer than incandescent bulbs, although they may all soon be replaced by LEDs, which are even brighter at a given wattage and cheaper. 2 varieties of sodium lamps are common: high-pressure lamps, which look yellow-white, and the rarer low-pressure lamps, which look orange. Turns out, while all light pollution is bad for astrophysics, the low-pressure sodium lamps are least bad because their contamination can be easily subtracted from telescope data. In a model of cooperation, the entire city of Tucson, Arizona, the nearest large municipality to the Kitt Peak National Observatory, has, by agreement with the local astrophysicists, converted all its streetlights to low-pressure sodium lamps. Aluminum occupies nearly 10% of Earth's crust, yet was unknown to the ancients and unfamiliar to our great-grandparents. The element was not isolated and identified until 1827 and did not enter common household use until the late 1960s, when tin cans and tinfoil yielded to aluminum cans and, of course, aluminum foil. I'd bet most old people you know still call it tin foil. Polished aluminum makes a near-perfect reflector of visible light and is the coating of choice for nearly all telescope mirrors today. Titanium is 1.7 times denser than aluminum, but it's more than twice as strong. So titanium, the 9th most abundant element in Earth's crust, has become a modern darling for many applications, such as military aircraft components and prosthetics that require a light, strong metal for their tasks. In most cosmic places, the number of oxygen atoms exceeds that of carbon. After every carbon atom has latched onto the available oxygen atoms, forming carbon monoxide or carbon dioxide, the leftover oxygen bonds with other things like titanium. The spectra of red stars are riddled with features traceable to titanium oxide, which itself is no stranger to stars on Earth. Star sapphires and rubies owe their radiant asterisms to titanium oxide impurities in their crystal lattice. Furthermore, the white paint used for telescope domes features titanium oxide, which happens to be highly reflective in the infrared part of the spectrum, greatly reducing the heat accumulated from sunlight in the air surrounding the telescope. At nightfall, with the dome open, the air temperature near the telescope rapidly equals the temperature of the nighttime air, allowing light from stars and other cosmic objects to be sharp and clear. And, while not directly named for a cosmic object, titanium derives from the Titans of Greek mythology. Titan is Saturn's largest moon. By many measures, iron ranks as the most important element in the universe. Massive stars manufacture elements in their core, in sequence from helium to carbon to oxygen to nitrogen and so forth, all the way up the periodic table to iron. With 26 protons and at least as many neutrons in its nucleus, iron's odd distinction comes from having the least total energy per nuclear particle of any element. This means something quite simple. If you split iron atoms via fission, they will absorb energy. And if you combine iron atoms via fusion, they will also absorb energy. Stars, however, are in the business of making energy. As high-mass stars manufacture and accumulate iron in their cores, they are nearing death. Without a fertile source of energy, the star collapses under its own weight and instantly rebounds in a stupendous supernova explosion, outshining 1 billion suns for more than a week. The soft metal gallium has such a low melting point that, like cocoa butter, it will liquefy on contact with your hand. Apart from this parlor demo, gallium is not interesting to astrophysicists except as one of the ingredients in the gallium chloride experiments used to detect elusive neutrinos from the sun. A huge 100-ton underground vat of liquid gallium chloride is monitored for any collisions between neutrinos and gallium nuclei, turning it into germanium. The encounter emits a spark of X-ray light that is measured every time a nucleus gets slammed. The long-standing solar neutrino problem, where fewer neutrinos were detected than predicted by solar theory, was solved using telescopes such as this. Every form of the element technetium is radioactive. Not surprisingly, it's found nowhere on Earth except in particle accelerators, where we make it on demand. Technetium carries this distinction in its name, which derives from the Greek teknetos, meaning artificial. For reasons not fully understood, technetium lives in the atmospheres of a select subset of red stars. This alone would not be cause for alarm, except that technetium has a half-life of a mere 2 million years, which is much, much shorter than the age and life expectancy of the stars in which it's found. In other words, the star cannot have been born with this stuff, for if it were, there would be none left by now. There is also no known mechanism to create technetium in a star's core and have it dredge itself up to the surface where it is observed, which has led to exotic theories that have yet to achieve consensus in the astrophysics community. Along with osmium and platinum, iridium is one of the 3 heaviest, densest elements on the table. 2 cubic feet of it weighs as much as a Buick, which makes iridium one of the world's best paperweights, able to defy all known office fans. Iridium is also the world's most famous smoking gun. A thin layer of it can be found worldwide at the famous Cretaceous-Paleogene boundary, formerly known as the KT boundary in geologic strata, dating from 65 million years ago. Not so coincidentally, that's when every land species larger than a carry-on suitcase went extinct, including the legendary dinosaurs. Iridium is rare on Earth's surface, but relatively common in 6-mile metallic asteroids, which, upon colliding with Earth, vaporized on impact, scattering their atoms across Earth's surface. So, whatever might have been your favorite theory for offing the dinosaurs, a killer asteroid the size of Mount Everest from outer space should be at the top of your list. I don't know how Albert would have felt about this, but an unknown element was discovered in the debris of the first hydrogen bomb test in the Eniwetok Atoll in the South Pacific on November 1st, 1952, and was named Einsteinium in his honor. I might have named it Armageddonium instead. Meanwhile, 10 entries in the periodic table get their names from objects that orbit the sun. Phosphorus comes from the Greek for light-bearing, and was the ancient name for the planet Venus when it appeared before sunrise in the dawn sky. Selenium comes from Selene, which is Greek for the moon, named so because in ores it was always associated with the element tellurium, which had already been named for Earth, from the Latin tellus. On January 1st, 1801, the Italian astronomer Giuseppe Piazzi discovered a new planet orbiting the Sun in the suspiciously large gap between Mars and Jupiter. Keeping with the tradition of naming planets after Roman gods, the object was named Ceres, after the goddess of harvest. Ceres is, of course, the root of the word cereal. At the time, there was sufficient excitement in the scientific community for the first element discovered after this date to be named cerium in its honor. 2 years later, another planet was discovered orbiting the Sun in the same gap as Ceres. This one was named Pallas, for the Roman goddess of wisdom. And, like cerium before it, the first element discovered thereafter was named palladium in its honor. The naming party would end a few decades later, after dozens more of these planets were discovered sharing the same orbital zone. Closer analysis revealed that these objects were much, much smaller than the smallest known planets. A new swath of real estate had been discovered in the solar system, populated by small, craggy chunks of rock and metal. Ceres and Pallas were not planets. They are asteroids, and they live in the asteroid belt, now known to contain hundreds of thousands of objects, somewhat more than the number of elements in the periodic table. The metal Mercury, liquid and runny at room temperature, and the planet Mercury, the fastest of all planets in the solar system, are both named for the speedy Roman messenger god of the same name. Thorium is named for Thor, the hunky lightning bolt-wielding Scandinavian god who corresponds with lightning bolt-wielding Jupiter in Roman mythology. And, by Jove, Hubble Space Telescope images of Jupiter's polar regions reveal extensive electrical discharges deep within its turbulent cloud layers. Alas, Saturn, my favorite planet, has no element named for it, but Uranus, Neptune, and Pluto are famously represented. The element uranium was discovered in 1789 and named in honor of the planet discovered by William Herschel just 8 years earlier. All isotopes of uranium are unstable, spontaneously decaying to lighter elements, a process accompanied by the release of energy. The first atomic bomb ever used in warfare had uranium as its active ingredient and was dropped by the United States, incinerating the Japanese city of Hiroshima on August 6, 1945. With 92 protons packed in its nucleus, uranium is widely described as the largest naturally occurring element, although trace amounts of larger elements can be found naturally where uranium ore is mined. If Uranus deserved an element named in its honor, then so did Neptune. Unlike uranium, however, which was discovered shortly after the planet, Neptunium was discovered in 1940 in the Berkeley cyclotron. A full 97 years after the German astronomer John Gall found Neptune in a spot on the sky predicted by the French mathematician Joseph Le Verrier after studying Uranus's odd orbital behavior. Just as Neptune comes right after Uranus in the solar system, so too does Neptunium come right after uranium in the periodic table of elements. The Berkeley cyclotron discovered or manufactured many elements not found in nature, including plutonium, which directly follows Neptunium in the table and was named for Pluto, which Clyde Tombaugh discovered at Arizona's Lowell Observatory in 1930. Just as with the discovery of Ceres 129 years earlier, excitement prevailed. Pluto was the first planet discovered by an American and, in the absence of better data, was widely regarded as an object of commensurate size and mass to Earth, if not Uranus or Neptune. As our attempts to measure Pluto's size became more and more refined, Pluto kept getting smaller and smaller. Our knowledge of Pluto's dimensions did not stabilize until the late 1980s. We now know that cold, icy Pluto is by far the smallest of the 9, with the diminutive distinction of being littler than the solar system's 6 largest moons. And like the asteroids, hundreds more objects were later discovered in the outer solar system, with orbits similar to that of Pluto, signaling the end of Pluto's tenure as a planet and the revelation of a heretofore undocumented reservoir of small icy bodies called the Kuiper Belt of comets, to which Pluto belongs. In this regard, one could argue that Ceres, Pallas, and Pluto slipped into the periodic table under false pretenses. Unstable, weapons-grade plutonium was the active ingredient in the atomic bomb that the United States exploded over the Japanese city of Nagasaki just 3 days after Hiroshima. bringing a swift end to World War II. Small quantities of non-weapons-grade radioactive plutonium can be used to power radioisotope thermoelectric generators, sensibly abbreviated as RTGs, for spacecraft that travel to the outer solar system, where the intensity of sunlight has diminished below the level usable by solar panels. 1 pound of plutonium will generate 10 million kilowatt hours of heat energy, which is enough to power an incandescent light bulb for 11,000 years. Or a human being for just as long if we ran on nuclear fuel instead of grocery store food. So ends our cosmic journey through the periodic table of elements, right to the edge of the solar system and beyond. For reasons I've yet to understand, many people don't like chemicals, which might explain the perennial movement to rid foods of them. Perhaps sesquipedalian chemical names just sound dangerous. But in that case, we should blame the chemists and not the chemicals themselves. Personally, I'm quite comfortable with chemicals anywhere in the universe. My favorite stars, as well as my best friends, are all made of them. Chapter 8. On Being Round. Apart from crystals and broken rocks, not much else in the cosmos naturally comes with sharp angles. While many objects have peculiar shapes, the list of round things is practically endless and ranges from simple soap bubbles to the entire observable universe. Of all shapes, spheres are favored by the action of simple physical laws. So prevalent is this tendency that often we assume something is spherical in a mental experiment just to glean basic insight, even when we know that the object is decidedly non-spherical. In short, if you do not understand the spherical case, then you cannot claim to understand the basic physics of the object. Spheres in nature are made by forces such as surface tension that want to make objects smaller in all directions. The surface tension of the liquid that makes a soap bubble squeezes air in all directions. It will, within moments of being formed, enclose the volume of air using the least possible surface area. This makes the strongest possible bubble, because the soapy film will not have to be spread any thinner than is absolutely necessary. Using freshman-level calculus, you can show that the one and only shape that has the smallest surface area for an enclosed volume is a perfect sphere. In fact, billions of dollars could be saved annually on packaging materials if all shipping boxes and all packages of food in the supermarket were spheres. For example, the contents of a super jumbo box of Cheerios would fit easily into a spherical carton with a 4.5-inch radius. But practical matters prevail. Nobody wants to chase packaged food down the aisle after it rolls off the shelves. On Earth, one way to make ball bearings is to machine them, or drop molten metal in pre-measured amounts into the top of a long shaft. The blob will typically undulate until it settles into the shape of a sphere, but it needs sufficient time to harden before hitting the bottom. On orbiting space stations where everything is weightless, you gently squirt out precise quantities of molten metal and you have all the time you need. The beads just float there while they cool until they harden as perfect spheres, with surface tension doing all the work for you. For large cosmic objects, energy and gravity conspire to turn objects into spheres. Gravity is the force that serves to collapse matter in all directions, but gravity does not always win. Chemical bonds of solid objects are strong. The Himalayas grew against the force of Earth's gravity because of the resilience of crustal rock. But before you get excited about Earth's mighty mountains, you should know that the spread in height from the deepest undersea trenches to the tallest mountains is about 12 miles, yet Earth's diameter is nearly 8,000 miles. So, contrary to what it looks like to teeny humans crawling on its surface, Earth as a cosmic object is remarkably smooth. If you had a super-duper jumbo gigantic finger and you dragged it across Earth's surface, oceans and all, Earth would feel as smooth as a cue ball. Expensive globes that portray raised portions of Earth's land masses to indicate mountain ranges are gross exaggerations of reality. This is why, in spite of Earth's mountains and valleys, As well as being slightly flattened from pole to pole, when viewed from space, Earth is indistinguishable from a perfect sphere. Earth's mountains are also puny when compared with some other mountains in the solar system. The largest on Mars, Olympus Mons, is 65,000 feet tall and nearly 300 miles wide at its base. It makes Alaska's Mount McKinley look like a molehill. The cosmic mountain building recipe is simple. The weaker the gravity on the surface of an object, the higher its mountains can reach. Mount Everest is about as tall as a mountain on Earth can grow before the lower rock layers succumb to their own plasticity under the mountain's weight. If a solid object has low enough surface gravity, chemical bonds in its rocks will resist the force of their own weight. When this happens, almost any shape is possible. Two famous celestial non-spheres are Phobos and Deimos, the Idaho potato-shaped moons of Mars. On 13-mile-long Phobos, the bigger of the two moons, a 150-pound person would weigh a mere 4 ounces. In space, surface tension always forces a small blob of liquid to form a sphere. Whenever you see a small, solid object that is suspiciously spherical, you can assume it formed in a molten state. If the blob has very high mass, then it could be composed of almost anything, and gravity will ensure that it forms a sphere. Big and massive blobs of gas in the galaxy can coalesce to form near-perfect gaseous spheres called stars. But if a star finds itself orbiting too close to another object whose gravity is significant, the spherical shape can be distorted as its material gets stripped away. By too close, I mean too close to the object's Roche lobe, named for the mid-19th century mathematician Édouard Roche, who made detailed studies of gravity fields in the vicinity of double stars. The Roche lobe is a theoretical dumbbell-shaped bulbous double envelope that surrounds any two objects in mutual orbit. If gaseous material from one object passes out of its own envelope, then the material will fall towards the second object. This occurrence is common among binary stars when one of them swells to become a red giant and overfills its Roche lobe. The red giant distorts into a distinctly non-spherical shape that resembles an elongated Hershey's Kiss. Moreover, every now and then, one of the two stars is a black hole, whose location is rendered visible by the flaying of its binary companion. The spiraling gas, after having passed from the giant across its Roche lobe, heats to extreme temperatures and is rendered aglow before descending out of sight into the black hole itself. The stars of the Milky Way galaxy trace a big, flat circle, with a diameter to thickness ratio of 1,000 to 1. Our galaxy is flatter than the flattest flapjacks ever made. In fact, its proportions are better represented by a crepe, or tortilla. No, the Milky Way's disk is not a sphere, but it probably began as one. We can understand the flatness by assuming the galaxy was once a big, spherical, slowly rotating ball of collapsing gas. During the collapse, the ball spun faster and faster, just as spinning figure skaters do when they draw their arms inward to increase their rotation rate. The galaxy naturally flattened pole to pole, while the increasing centrifugal forces in the middle prevented collapse at mid-plane. Yes, if the Pillsbury Doughboy were a figure skater, then fast spins would be a high-risk activity. Any stars that happen to be formed within the Milky Way cloud before collapse maintained large plunging orbits. The remaining gas, which easily sticks to itself like a mid-air collision of two hot marshmallows, got pinned at the midplane and is responsible for all subsequent generations of stars, including the Sun. The current Milky Way, which is neither collapsing nor expanding, is a gravitationally mature system, where one can think of the orbiting stars above and below the disk as the skeletal remains of the original spherical gas cloud. This general flattening of objects that rotate is why Earth's pole-to-pole diameter is smaller than its diameter at the equator. Not by much, 0.3%, about 26 miles. But Earth is small, mostly solid, and doesn't rotate all that fast. At 24 hours per day, Earth carries anything on its equator at a mere 1,000 miles per hour. Consider the jumbo, fast-rotating gaseous planet Saturn, completing a day in just 10.5 hours. Its equator revolves at 22,000 miles per hour, and its pole-to-pole dimension is a full 10% flatter than its middle, a difference noticeable even through a small amateur telescope. Flattened spheres are more generally called oblate spheroids, while spheres that are elongated pole-to-pole are called prolate. In everyday life, hamburgers and hot dogs make excellent, although somewhat extreme examples of each shape. I don't know about you, but the planet Saturn pops into my mind with every bite of a hamburger I take. We use the effect of centrifugal forces on matter to offer insight into the rotation rate of extreme cosmic objects. Consider pulsars. With some rotating at upward of 1,000 revolutions per second, we know that they cannot be made of household ingredients, or they would spin themselves apart. In fact, if a pulsar rotated any faster, say 4,500 revolutions per second, its equator would be moving at the speed of light, which tells you that this material is unlike any other. To picture a pulsar, imagine the mass of the sun packed into a ball the size of Manhattan. If that's hard to do, then maybe it's easier for you to imagine stuffing about 100 million elephants into a chapstick casing. To reach this density, you must compress all the empty space that atoms enjoy around their nucleus and among their orbiting electrons. Doing so will crush nearly all negatively charged electrons into positively charged protons, creating a ball of neutrally charged neutrons with a crazy high surface gravity. Under such conditions, a neutron star's mountain range needn't be any taller than the thickness of a sheet of paper for you to exert more energy climbing it than a rock climber on Earth would exert ascending a 3,000-mile-high cliff. In short, where gravity is high, the high places tend to fall, filling in the low places, a phenomenon that sounds almost biblical in preparing the way for the Lord. Every valley shall be raised up, every mountain and hill made low. The rough ground shall be made level, the rugged places a plain. Isaiah chapter 40, verse 4. That's a recipe for a sphere if there ever was one. For all these reasons, we expect pulsars to be the most perfectly shaped spheres in the universe. For rich clusters of galaxies, the overall shape can offer deep astrophysical insight. Some are raggedy, others are stretched thin in filaments, yet others form vast sheets. None of these have settled into a stable, spherical gravitational shape. Some are so extended that the 14 billion-year age of the universe is insufficient time for their constituent galaxies to make one crossing of the cluster. We conclude that the cluster was born that way, because the mutual gravitational encounters between and among galaxies have had insufficient time to influence the cluster's shape. But other systems, such as the beautiful Coma cluster of galaxies, which we met in our chapter on dark matter, tells us immediately that gravity has shaped the cluster into a sphere. As a consequence, you are as likely to find a galaxy moving in one direction as in any other. Whenever this is true, the cluster cannot be rotating all that fast. Otherwise, we would see some flattening as we do in our own Milky Way. The Coma cluster, once again like the Milky Way, is also gravitationally mature. In astrophysical vernacular, such systems are said to be relaxed, which means many things, including the fortuitous fact that the average velocity of galaxies in the cluster serves as an excellent indicator of the total mass. Whether or not the total mass of the system is supplied by the objects used to get the average velocity. It's for these reasons that gravitationally relaxed systems make excellent probes of non-luminous dark matter. Allow me to make an even stronger statement. Were it not for relaxed systems, the ubiquity of dark matter may have remained undiscovered to this day. The sphere to end all spheres, the largest and most perfect of them all, is the entire observable universe. In every direction we look, galaxies recede from us at speeds proportional to their distance. As we saw in the first few chapters, this is the famous signature of an expanding universe, discovered by Edwin Hubble in 1929. When you combine Einstein's relativity and the velocity of light and the expanding universe and the spatial dilution of mass and energy as a consequence of that expansion, there is a distance in every direction from us, where the recession velocity for a galaxy equals the speed of light. At this distance and beyond, light from all luminous objects loses all its energy before reaching us. The universe beyond this spherical edge is thus rendered invisible and, as far as we know, unknowable. There's a variation of the ever-popular multiverse idea in which the multiple universes that comprise it are not separate universes entirely, but isolated, non-interacting pockets of space within one continuous fabric of space-time. Like multiple ships at sea, far enough away from one another so that their circular horizons do not intersect. As far as any one ship is concerned, without further data, it's the only ship on the ocean, yet they all share the same body of water. Spheres are indeed fertile theoretical tools that help us gain insight into all manner of astrophysical problems. But one should not be a sphere zealot. I'm reminded of the half-serious joke about how to increase milk production on a farm. An expert in animal husbandry might say, consider the role of the cow's diet. An engineer might say, consider the design of the milking machines. But it's the astrophysicist who says, consider a spherical cow. Chapter 9. Invisible Light. And therefore, as a stranger, give it welcome. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. Hamlet, Act 1, Scene 5. Before 1800, the word light, apart from its use as a verb and an adjective, referred just to visible light. But early that year, the English astronomer William Herschel observed some warming that could only have been caused by a form of light invisible to the human eye. Already an accomplished observer, Herschel had discovered the planet Uranus in 1781 and was now exploring the relation between sunlight, color, and heat. He began by placing a prism in the path of a sunbeam. Nothing new there. Sir Isaac Newton had done that back in the 1600s, leading him to name the familiar 7 colors of the visible spectrum: red, orange, yellow, green, blue, indigo, and violet. Yes, the colors do indeed spell Roy G. Biv. But Herschel was inquisitive enough to wonder what the temperature of each color might be. So he placed thermometers in various regions of the rainbow and showed, as he suspected, that different colors registered different temperatures. Well-conducted experiments require a control, a measurement where you expect no effect at all and which serves as a kind of idiot check on what you are measuring. For example, if you wonder what effect beer has on a tulip plant, then also nurture a second tulip plant identical to the first, but give it water instead. If both plants die, if you killed them both, then you can't blame the alcohol. That's the value of a control sample. Herschel knew this and laid a thermometer outside of the spectrum, adjacent to the red, expecting to read no more than room temperature throughout the experiment. But that's not what happened. The temperature of his control thermometer rose even higher than in the red. Herschel wrote, "I conclude that the full red falls still short of the maximum of heat, which perhaps lies even a little beyond visible refraction. In this case, radiant heat will at least partly, if not chiefly, consist, if I may be permitted the expression, of invisible light. That is to say, of rays coming from the sun that have such a momentum as to be unfit for vision." Holy shit! Herschel inadvertently discovered infrared light, a brand new part of the spectrum found just below red, reported in the first of his 4 papers on the subject. Herschel's revelation was the astronomical equivalent of Antony von Leeuwenhoek's discovery of, quote, many little living animalcules, very prettily a-moving, in the smallest drop of lake water. Leeuwenhoek discovered single-celled organisms, a biological universe. Herschel discovered a new band of light, both hiding in plain sight. Other investigators immediately took up where Herschel left off. In 1801, the German physicist and pharmacist Johann Wilhelm Ritter found yet another band of invisible light. But instead of a thermometer, Ritter placed a little pile of light-sensitive silver chloride in each visible color, as well as in the dark area next to the violet end of the spectrum. Sure enough, the pile in the unlit patch darkened more than the pile in the violet patch. What's beyond violet? Ultraviolet, better known today as UV. Filling out the entire electromagnetic spectrum in order of low energy and low frequency to high energy and high frequency, we have radio waves, microwaves, infrared, Roy G. Biv, ultraviolet, X-rays, and gamma rays. Modern civilization has deftly exploited each of these bands for countless household and industrial applications, making them familiar to us all. After the discovery of UV and IR, skywatching didn't change overnight. The first telescope designed to detect invisible parts of the electromagnetic spectrum wouldn't be built for 130 years. That's well after radio waves, X-rays, and gamma rays had been discovered, and well after the German physicist Heinrich Hertz had shown that the only real difference among the various kinds of light is the frequency of the waves in each band. In fact, credit Hertz for recognizing that there is such a thing as an electromagnetic spectrum. In his honor, the unit of frequency in waves per second for anything that vibrates, including sound, has duly been named the Hertz. Mysteriously, astrophysicists were a bit slow to make the connection between the newfound invisible bands of light and the idea of building a telescope that might see those bands from cosmic sources. Delays in detector technology surely mattered here, but hubris must take some of the blame. How could the universe possibly send us light that our marvelous eyes cannot see? For more than 3 centuries, from Galileo's day until Edwin Hubble's, building a telescope meant only one thing: making an instrument to catch visible light, enhancing our biologically endowed vision. A telescope is merely a tool to augment our meager senses, enabling us to get better acquainted with faraway places. The bigger the telescope, the dimmer the objects it brings into view. The more perfectly shaped its mirrors, the sharper the image it makes. The more sensitive its detectors, the more efficient its observations. But in all cases, every bit of information a telescope delivers to the astrophysicist comes to Earth on a beam of light. Celestial happenings, however, don't limit themselves to what's convenient for the human retina. Instead, they typically emit varying amounts of light simultaneously in multiple bands. So without telescopes and their detectors tuned across the entire spectrum, astrophysicists would remain blissfully ignorant of some mind-blowing stuff in the universe. Take an exploding star, a supernova. It's a cosmically common and seriously high-energy event that generates prodigious quantities of X-rays. Sometimes, bursts of gamma rays and flashes of ultraviolet accompany the explosions, and there's never a shortage of visible light. Long after the explosive gases cool, the shock waves dissipate, and the visible light fades, the supernova remnant keeps on shining in the infrared while pulsing in radio waves. That's where pulsars come from, the most reliable timekeepers in the universe. Most stellar explosions take place in distant galaxies, but if a star were to blow up within the Milky Way, its death throes would be bright enough for everyone to see, even without a telescope. But nobody on Earth saw the invisible X-rays or gamma rays from the last 2 supernova spectaculars hosted by our galaxy. One in 1572 and another in 1604. Yet their wondrous visible light was widely reported. The range of wavelengths, or frequencies that comprise each band of light, strongly influences the design of the hardware used to detect it. That's why no single combination of telescope and detector can simultaneously see every feature of such explosions. But the way around that problem is simple. gather all observations of your object, perhaps obtained by colleagues in multiple bands of light. Then assign visible colors to invisible bands of interest, creating one meta multi-band image. That's precisely what Geordi from the television series Star Trek The Next Generation sees. With that power of vision, you miss nothing. Only after you identify the band of your astrophysical affections can you begin to think about the size of your mirror, the materials you'll need to make it, the shape and surface it must have, and the kind of detector you'll need. X-ray wavelengths, for example, are extremely short, so if you're accumulating them, your mirror had better be super smooth, lest imperfections in the surface distort them. But if you're gathering long radio waves, your mirror could be made of chicken wire that you've bent with your hands, because the irregularities in the wire would be much smaller than the wavelengths you're after. Of course, you also want plenty of detail, high resolution, so your mirror should be as big as you can afford to make it. In the end, your telescope must be much, much wider than the wavelength of light you aim to detect. And nowhere is this need more evident than in the construction of a radio telescope. Radio telescopes, the earliest non-visible light telescopes ever built, are an amazing subspecies of observatory. The American engineer Carl G. Jansky built the first successful one between 1929 and 1930. It looked a bit like the moving sprinkler system on a farmerless farm, made from a series of tall rectangular metal frames secured with wooden cross supports and flooring. It turned in place like a merry-go-round, but on wheels built with spare parts from a Model T Ford. Jansky had tuned the 100-foot-long contraption to a wavelength of about 15 meters, corresponding to a frequency of 20.5 megahertz. Jansky's agenda, on behalf of his employer, Bell Telephone Laboratories, was to study any hisses from Earth-based radio sources that might contaminate terrestrial radio communications. This greatly resembles the task that Bell Labs gave Penzias and Wilson 35 years later, to find microwave noise in their receiver, as we heard in Chapter 3, which led to the discovery of the cosmic microwave background. By spending a couple of years painstakingly tracking and timing the static hiss that registered in his jury-rigged antenna, Jansky had discovered that radio waves emanate not just from local thunderstorms and other known terrestrial sources, but also from the center of the Milky Way galaxy. That region of the sky swung by the telescope's field of view every 23 hours and 56 minutes, exactly the period of Earth's rotation in space, and thus exactly the time needed to return the galactic center to the same angle and elevation on the sky. Carl Jansky published his results under the title Electrical Disturbances, apparently of extraterrestrial origin. With that observation, radio astronomy was born. But minus Jansky himself, Bell Labs retasked him, preventing him from pursuing the fruits of his own seminal discovery. A few years later, though, a self-starting American named Grote Reber from Wheaton, Illinois, built a 30-foot-wide metal dish radio telescope in his own backyard. In 1938, under nobody's employ, Reber confirmed Jansky's discovery and spent the next 5 years making low-resolution maps of the radio sky. Reber's telescope was small and crude by today's standards. Modern radio telescopes are quite another matter. Unbound by backyards, they're sometimes downright humongous. MK1, which began its working life in 1957, is the planet's first genuinely gigantic radio telescope. A single steerable 250-foot-wide solid steel dish at the Jodrell Bank Observatory near Manchester, England. A couple of months after MK1 opened for business, the Soviet Union launched Sputnik 1, and Jodrell Bank's dish suddenly became just the thing to track the little orbiting hunk of hardware, making it the forerunner of today's deep space network for tracking planetary space probes. The world's largest radio telescope, completed in 2016, is called the 500-meter Aperture Spherical Radio Telescope, or FAST for short. It was built by China in their Guizhou province and is larger in area than 30 football fields. If aliens ever give us a call, The Chinese will be the first to know. Another variety of radio telescope is the interferometer, comprising arrays of identical dish antennas spread across swaths of countryside and electronically linked to work in concert. The result is a single coherent super high-resolution image of radio-emitting cosmic objects. Although "Supersize Me" was the unwritten motto for telescopes long before the fast food industry coined the slogan, radio interferometers form a jumbo class unto themselves. One of them, a very large array of radio dishes near Socorro, New Mexico, is officially called the Very Large Array, with 27 82-foot dishes positioned on tracks crossing 22 miles of desert plains. This observatory is so cosmogenic, it has appeared as a backdrop in the films 2010, The Year We Made Contact, 1984, Contact, 1997, and The Transformers, 2007. There's also the Very Long Baseline Array, with 10 82-foot dishes spanning 5,000 miles from Hawaii to the Virgin Islands, enabling the highest resolution of any radio telescope in the world. In the microwave band, relatively new to interferometers, we've got the 66 antennas of ALMA, the Atacama Large Millimeter Array in the remote Andes Mountains of northern Chile. Tuned for wavelengths that range from fractions of a millimeter to several centimeters, ALMA gives astrophysicists high-resolution access to categories of cosmic action unseen in other bands, such as the structure of collapsing gas clouds as they become nurseries from which stars are born. ALMA's location is, by intention, the most arid landscape on Earth, 3 miles above sea level and well above the wettest clouds. Water may be fine for microwave cooking, but it's bad for astrophysicists because the water vapor in Earth's atmosphere chews up pristine microwave signals from across the galaxy and beyond. These two phenomena are, of course, related. Water is the most common ingredient in food, and microwave ovens primarily heat water. Taken together, you get the best indication that water absorbs microwave frequencies. So if you want clean observations of cosmic objects, you must minimize the amount of water vapor between your telescope and the universe, just as ALMA has done. At the ultra-short wavelength end of the electromagnetic spectrum, you find the high-frequency, high-energy gamma rays, with wavelengths measured in picometers. That's trillionths of a meter. Discovered in 1900, they were not detected from space until a new kind of telescope was placed aboard NASA's Explorer 11 satellite in 1961. Anybody who watches too many sci-fi movies knows that gamma rays are bad for you. You might turn green and muscular, or spider webs might squirt from your wrists, but they're also hard to trap. They pass right through ordinary lenses and mirrors. How then to observe them? The guts of Explorer 11's telescope held a device called a scintillator, which responds to incoming gamma rays by pumping out electrically charged particles. If you measure energies of the particles, you can tell what kind of high-energy light created them. 2 years later, the Soviet Union, the United Kingdom, and the United States signed the Limited Test Ban Treaty, which prohibited nuclear testing underwater, in the atmosphere, and in space, where nuclear fallout could spread and contaminate places outside your own country's perimeter. But this was the Cold War, a time when nobody believed anybody about anything. Invoking the military edict, Trust But Verify, the U.S. deployed a new series of satellites, the Velas, to scan for gamma-ray bursts that would result from Soviet nuclear tests. The satellites indeed found bursts of gamma rays almost daily, but Russia wasn't to blame. These came from deep space and were later shown to be the calling card of intermittent, distant, titanic stellar explosions across the universe, signaling the birth of gamma-ray astrophysics, a new branch of study in my field. In 1994, NASA's Compton Gamma Ray Observatory detected something as unexpected as the Velas discoveries: frequent flashes of gamma rays right near Earth's surface. They were sensibly dubbed terrestrial gamma ray flashes. Nuclear holocaust? No, as is evident from the fact that you're reading the sentence. Not all bursts of gamma rays are equally lethal, nor are they all of cosmic origin. In this case, at least 50 flashes emanate daily near the tops of thunderclouds, a split second before ordinary lightning bolts strike. Their origin remains a bit of a mystery, but the best explanation holds that in the electrical storm, free electrons accelerate to near the speed of light and then slam into the nuclei of atmospheric atoms, generating gamma rays. Today, telescopes operate in every invisible part of the spectrum, some from the ground, but most from space, where a telescope's view is unimpeded by Earth's absorptive atmosphere. We can now observe phenomena ranging from low-frequency radio waves a dozen meters across, crest to crest, to high-frequency gamma rays, no longer than a quadrillionth of a meter. That rich palette of light supplies no end of astrophysical discoveries. Curious how much gas lurks among the stars and galaxies? Radio telescopes do that best. There is no knowledge of the cosmic background and no real understanding of the Big Bang without microwave telescopes. Want to peek at the stellar nurseries deep inside galactic gas clouds? Pay attention to what infrared telescopes do. How about emissions from the vicinity of ordinary black holes and supermassive black holes in the center of a galaxy? Ultraviolet and X-ray telescopes do that best. Want to watch the high-energy explosion of a giant star whose mass is as great as 40 suns? Catch the drama via gamma-ray telescopes. We've come a long way since Herschel's experiments with rays that were unfit for vision, empowering us to explore the universe for what it is, rather than for what it seems to be. Herschel would be proud. We achieved true cosmic vision only after seeing the unseeable. A dazzlingly rich collection of objects and phenomena across space and across time that we may now dream of in our philosophy. Chapter 10. Between the Planets. From a distance, our solar system looks empty. If you enclosed it within a sphere, one large enough to contain the orbit of Neptune, the outermost planet, then the volume occupied by the Sun, all the planets, and their moons would take up a little more than 1/trillionth the enclosed space. But it's not empty. The space between the planets contains all manner of chunky rocks, pebbles, ice balls, dust, streams of charged particles, and far-flung probes. The space is also permeated by monstrous gravitational and magnetic fields. Interplanetary space is so not empty that Earth, during its 30-kilometer-per-second orbital journey, plows through hundreds of tons of meteors per day, most of them no larger than a grain of sand. Nearly all of them burn in Earth's upper atmosphere, slamming into the air with so much energy that the debris vaporizes on contact. Our frail species evolved under this protective blanket. Larger golf ball-sized meteors heat fast but unevenly and often shatter into many smaller pieces before they vaporize. Still larger meteors singe their surface, but otherwise make it all the way to the ground intact. You'd think that by now, after 4.6 billion trips around the Sun, Earth would have vacuumed up all possible debris in its orbital path. But things were once much worse. For 500 million years after the formation of the Sun and its planets, so much junk rained down on Earth that heat from the persistent energy of impacts rendered Earth's atmosphere hot and our crust molten. One substantial hunk of junk led to the formation of the Moon. The unexpected scarcity of iron and other high-mass elements in the Moon, derived from lunar samples returned by Apollo astronauts, indicates that the Moon most likely burst forth from Earth's iron-poor crust and mantle after a glancing collision with a wayward Mars-sized protoplanet. The orbiting debris from this encounter coalesced to form our lovely low-density satellite. Apart from this newsworthy event, the period of heavy bombardment that Earth endured during its infancy was not unique among the planets and other large bodies of the solar system. They each sustained similar damage, with the airless, erosionless surfaces of the Moon and Mercury preserving much of the cratered record from this period. Not only is the solar system scarred by the flotsam of its formation, but nearby interplanetary space also contains rocks of all sizes that were jettisoned from Mars, the Moon, and Earth by the ground's recoil from high-speed impacts. Computer studies of meteor strikes demonstrate conclusively that surface rocks near impact zones can get thrust upward with enough speed to escape the body's gravitational tether. At the rate we are discovering meteorites on Earth whose origin is Mars, we conclude that about 1,000 tons of Martian rocks rain down on Earth each year. Perhaps the same amount reaches Earth from the Moon. In retrospect, we didn't have to go to the Moon to retrieve moon rocks. Plenty come to us, although they were not of our choosing, and we didn't yet know it during the Apollo program. Most of the solar system's asteroids live and work in the main asteroid belt, a roughly flat zone between the orbits of Mars and Jupiter. By tradition, the discoverers get to name their asteroids whatever they like, often drawn by artists as a region of cluttered, meandering rocks in the plane of the solar system. The asteroid belt's total mass is less than 5% that of the Moon, which is itself barely more than 1% of Earth's mass. Sounds insignificant, but accumulated perturbations of their orbits continually create a deadly subset, perhaps a few thousand, whose eccentric paths intersect Earth's orbit. A simple calculation reveals that most of them will hit Earth within 100 million years. The ones larger than about a kilometer across will collide with enough energy to destabilize Earth's ecosystem and put most of Earth's land species at risk of extinction. That would be bad. Asteroids are not the only space objects that pose a risk to life on Earth. The Kuiper Belt is a comet-strewn swath of circular real estate that begins just beyond the orbit of Neptune, includes Pluto, and extends perhaps as far again from Neptune as Neptune is from the Sun. The Dutch-born American astronomer Gerard Kuiper advanced the idea that in the cold depths of space beyond the orbit of Neptune, there reside frozen leftovers from the formation of the solar system. Without a massive planet upon which to fall, most of these comets will orbit the Sun for billions of years. As is true for the asteroid belt, some objects of the Kuiper Belt travel on eccentric paths that cross the orbits of other planets. Pluto and its ensemble of siblings called Plutinos cross Neptune's path around the Sun. Other Kuiper Belt objects plunge all the way down to the inner solar system, crossing planetary orbits with abandon. This subset includes Halley, the most famous comet of them all. Far beyond the Kuiper Belt, extending halfway to the nearest stars, lives a spherical reservoir of comets called the Oort cloud, named for Jan Oort, the Dutch astrophysicist who first deduced its existence. This zone is responsible for the long-period comets, those with orbital periods far longer than a human lifetime. Unlike Kuiper Belt comets, Oort cloud comets can rain down on the inner solar system from any angle and from any direction. The two brightest of the 1990s, comets Hale-Bopp and Hyakutake, were both from the Oort cloud and are not coming back anytime soon. If we had eyes that could see magnetic fields, Jupiter would look 10 times larger than the full moon in the sky. Spacecraft that visit Jupiter must be designed to remain unaffected by this powerful force. As the English physicist Michael Faraday demonstrated in the 1800s, if you pass a wire across a magnetic field, you generate a voltage difference along the wire's length. For this reason, fast-moving metal space probes will have electrical currents induced within them. Meanwhile, these currents generate magnetic fields of their own that interact with the ambient magnetic field in ways that retard the space probe's motion. Last I had kept count, there were 56 moons among the planets in the solar system. Then I woke up one morning to learn that another dozen had been discovered around Saturn. After that incident, I decided to no longer keep track. All I care about now is whether any of them would be fun places to visit or to study. By some measures, the solar system's moons are more fascinating than the planets they orbit. Earth's moon is about 1/400th the diameter of the Sun, but it's also 1/400th as far from us, making the Sun and the moon the same size on the sky. A coincidence not shared by any other planet-moon combination in the solar system, allowing for uniquely photogenic total solar eclipses. Earth also has tidally locked the moon, leaving it with identical periods of rotation on its axis and revolution around Earth. Wherever and whenever this happens, the locked moon shows only one face to its host planet. Jupiter's system of moons is replete with oddballs. Io, Jupiter's closest moon, is tidally locked and structurally stressed by interactions with Jupiter and with other moons, pumping enough heat into the little orb to render molten its interior rocks. Io is the most volcanically active place in the solar system. Jupiter's moon Europa has enough H2O that its heating mechanism, the same one at work on Io, has melted the subsurface ice, leaving a warmed ocean below. If ever there was a next best place to look for life, it's here. An artist coworker of mine once asked whether alien life forms from Europa would be called Europeans. The absence of any other plausible answer forced me to say yes. Pluto's largest moon, Charon, is so big and close to Pluto that Pluto and Charon have each tidally locked the other. Their rotation periods and their periods of revolution are identical. We call this a double tidal lock, which sounds like a yet-to-be-invented wrestling hold. By convention, moons are named for Greek personalities in the life of the Greek counterpart to the Roman god after whom the planet itself was named. The classical gods led complicated social lives, so there's no shortage of characters from which to draw. The lone exception to this rule applies to the moons of Uranus, which are named for assorted protagonists in British lit. William Herschel was the first person to discover a planet beyond those easily visible to the naked eye, and he was ready to name it after the king, under whom he faithfully served. Had Herschel succeeded, the planet list would read Mercury, Venus, Earth, Mars, Jupiter, Saturn, and George. Fortunately, clearer heads prevailed and the classical name Uranus was adopted some years later. But his original suggestion to name the moons after characters in William Shakespeare's plays and Alexander Pope's poems remains the tradition to this day. Among its 27 moons, we find Ariel, Cordelia, Desdemona, Juliet, Ophelia, Portia, Puck, Umbriel, and Miranda. The Sun loses material from its surface at a rate of more than 1 million tons per second. We call this the solar wind, which takes the form of high-energy charged particles. Traveling up to 1,000 miles per second, these particles stream through space and are deflected by planetary magnetic fields. The particles spiral down toward the north and south magnetic poles, forcing collisions with gas molecules and leaving the atmosphere aglow with colorful aurora. The Hubble Space Telescope has spotted aurora near the poles of both Saturn and Jupiter. And on Earth, the aurora borealis and australis, the northern and southern lights, serve as intermittent reminders of how nice it is to have a protective atmosphere. Earth's atmosphere is commonly described as extending dozens of miles above Earth's surface. Satellites in low Earth orbit typically travel between 100 and 400 miles up, completing an orbit in about 90 minutes. While you can't breathe at those altitudes, some atmospheric molecules remain, enough to slowly drain orbital energy from unsuspecting satellites. To combat this drag, satellites in low orbit require intermittent boosts, lest they fall back to Earth and burn up in the atmosphere. An alternative way to define the edge of our atmosphere is to ask where its density of gas molecules equals the density of gas molecules in interplanetary space. Under that definition, Earth's atmosphere extends thousands of miles. Orbiting high above this level, 23,000 miles up, 1/10 of the distance to the Moon, are the communication satellites. At this special altitude, Earth's atmosphere is not only irrelevant, but the speed of the satellite is low enough for it to require a full day to complete one revolution around Earth. With an orbit precisely matching the rotation rate of Earth, these satellites appear to hover, which make them ideal for relaying signals from one part of Earth's surface to another. Newton's laws specifically state that while the gravity of a planet gets weaker and weaker the farther from it you travel, there is no distance where the force of gravity reaches zero. The planet Jupiter, with its mighty gravitational field, bats out of harm's way many comets that would otherwise wreak havoc on the inner solar system. Jupiter acts as a gravitational shield for Earth, a burly big brother, allowing long 100-million-year stretches of relative peace and quiet on Earth. Without Jupiter's protection, complex life would have a hard time becoming interestingly complex, always living at risk of extinction from a devastating impact. We have exploited the gravitational fields of planets for nearly every probe launched into space. The Cassini probe, for example, which visited Saturn, was gravitationally assisted twice by Venus, once by Earth on a return flyby, and once by Jupiter. Like a multi-cushion billiard shot, trajectories from one planet to another are common. Our tiny probes would not otherwise have enough speed and energy from our rockets to reach their destination. I am now accountable for some of the solar system's interplanetary debris. In November 2000, the main belt asteroid 1994 Ka, discovered by David Levy and Carolyn Shoemaker, was named 13123 Tyson in my honor. While I enjoyed the distinction, there's no particular reason to get big-headed about it. Plenty of asteroids have familiar names, such as Jody, Harriet, and Thomas. There are even asteroids out there named Merlin, James Bond, and Santa. Now, in the hundreds of thousands, the asteroid count might soon challenge our capacity to name them. Whether or not that day arrives, I take comfort knowing that my chunk of cosmic debris is not alone as it litters the space between the planets, being joined by a long list of other chunks named for real and fictional people. I'm also glad that, at the moment, my asteroid is not headed towards Earth. Chapter 11. Exoplanet Earth. Whether you prefer to sprint, swim, walk, or crawl from one place to another on Earth, you can enjoy close-up views of our planet's unlimited supply of things to notice. You might see a vein of pink limestone on the wall of a canyon, a ladybug eating an aphid on the stem of a rose, a clamshell poking out from the sand. All you have to do is look. From the window of an ascending jetliner, those surface details rapidly disappear. No aphid appetizers, no curious clams. Reach cruising altitude around 7 miles up, and identifying major roadways becomes a challenge. Detail continues to vanish as you rise into space. From the window of the International Space Station, which orbits about 250 miles up, you might find Paris, London, New York, and Los Angeles in the daytime, but only because you learned where they are in geography class. At night, their sprawling cityscapes present an obvious glow. By day, contrary to common wisdom, you probably won't see the Great Pyramids at Giza, and you certainly won't see the Great Wall of China. Their obscurity is partly the result of having been made from the soil and stone of the surrounding landscape. And although the Great Wall is thousands of miles long, it's only about 20 feet wide, much narrower than the U.S. interstate highways you can barely see from a transcontinental jet. From orbit, with the unaided eye, you would have seen smoke plumes rising from the oil field fires in Kuwait at the end of the First Persian Gulf War in 1991, and smoke from the burning World Trade Center towers in New York City on September 11, 2001. You will also notice the green-brown boundaries between swaths of irrigated and arid land. Beyond that short list, there's not much else made by humans that's identifiable from hundreds of miles up in the sky. You can see plenty of natural scenery, though, including hurricanes in the Gulf of Mexico, ice flows in the North Atlantic, and volcanic eruptions wherever they occur. From the moon, 250,000 miles away, New York, Paris, and the rest of Earth's urban glitter doesn't even show up as a twinkle. But from your lunar vantage, you can still watch major weather fronts move across the planet. From Mars, at its closest, some 35 million miles away, massive snow-capped mountain chains and the edges of Earth's continents would be visible through a large backyard telescope. Travel out to Neptune, 3 billion miles away, just down the block on a cosmic scale, and the sun itself becomes 1,000 times dimmer, now occupying 1,000th the area on the daytime sky that it occupies when seen from Earth. And what of Earth itself? It's a speck, no brighter than a dim star, all but lost in the glare of the sun. A celebrated photograph taken in 1990 from just beyond Neptune's orbit by the Voyager 1 spacecraft shows just how underwhelming Earth looks from deep space. A pale blue dot, as the American astrophysicist Carl Sagan called it. And that's generous. Without the help of a caption, you might not even know it's there. What would happen if some big-brained aliens from the great beyond scanned the skies with their naturally superb visual organs, further aided by alien state-of-the-art optical accessories? What visible features of planet Earth might they detect? Blueness would be first and foremost. Water covers more than 2/3 of Earth's surface. The Pacific Ocean alone spans nearly an entire side of the planet. Any beings with enough equipment and expertise to detect our planet's color would surely infer the presence of water, the third most abundant molecule in the universe. If the resolution of their equipment were high enough, the aliens would see more than just a pale blue dot. They would see intricate coastlines, too, strongly suggesting that the water is liquid. And smart aliens would surely know that if a planet has liquid water, then the planet's temperature and atmospheric pressure fall within a well-determined range. Earth's distinctive polar ice caps, which grow and shrink from the seasonal temperature variations, could also be seen using visible light. So could our planet's 24-hour rotation, because recognizable landmasses rotate into view at predictable intervals of time. The aliens would also see major weather systems come and go. With careful study, they could readily distinguish features related to clouds in the atmosphere from features related to the surface of Earth itself. Time for a reality check. The nearest exoplanet, the nearest planet in orbit around a star that is not the Sun, can be found in our neighbor star system, Alpha Centauri, about 4 light-years from us and visible mostly from our southern hemisphere. Most of the cataloged exoplanets lie from dozens up to hundreds of light-years away. Earth's brightness is less than 1/billionth that of the Sun, and our planet's proximity to the Sun would make it extremely hard for anybody to see Earth directly with a visible light telescope. It's like trying to detect the light of a firefly in the vicinity of a Hollywood searchlight. So if aliens have found us, they are likely looking in wavelengths other than visible light, like infrared, where our brightness relative to the Sun is a bit better than invisible light. Or else their engineers are adapting some other strategy altogether. Maybe they're doing what some of our own planet hunters typically do, monitoring stars to see if they jiggle at regular intervals. A star's periodic jiggle betrays the existence of an orbiting planet that may be too dim to see directly. Contrary to what most people suppose, a planet does not orbit its host star. Instead, both the planet and its host star revolve around their common center of mass. The more massive the planet, the larger the star's response must be, and the more measurable the jiggle gets when you analyze the star's light. Unfortunately for planet-hunting aliens, Earth is puny, so the Sun barely budges, which would further challenge alien engineers.